So in this video, we'll learn how to actually, so this is what we want to arrive at. Imagine if I have a microprocessor and a RAM chip, how do we now connect both of them, right? So that's called as CPU memory interfacing, right? This is what we want to understand. But before we go and understand how we interface, interfacing basically means how do you connect both these components? Before we go ahead and understand how a microprocessor, a very popular microprocessor like 8085 is interfaced with a RAM, let's understand a few simple concepts, right? While understanding these concepts, I will use these two microprocessors as simple examples. So there is this microprocessor called 8085, one of the most popular and one of the early microprocessors of Intel, which became very popular. 8085A is a small variation on 8085. So 8085A is a 8-bit microprocessor, right? So you can easily see that because if you look at this, again, I'll come to the data part, address part, all of that stuff, right? So this is an 8-bit microprocessor. Again, this is the pin diagram. There is another very popular microprocessor called 8086, which came after 8085. Remember, your 8085s, 8086 are much older microprocessors from Intel than your i3s, i5s, i7s, etc. Right? So these are old ones, but they are also simple for us to understand. If I start explaining you the architecture of i7 processor or an i5 processor, there are too many pins in it, which will confuse you, right? So first, let's understand the basics using these simple chips, or one of the first and the earliest Intel chips, which are still, all the concepts of computer organizational architecture can be learned from these chips themselves, right? Again, some of you may have courses where you learn about 8085 processor and 8086 processor also, called microprocessors course, right? So again, this is the pin diagram. 8086 is a 16-bit processor. Okay, I'll keep using these two processors as examples. First, let's learn about something called as a pin structure. So there are three broad types of pin structures. One is called active low, other is called active high, the third is called time multiplexed pins. Okay, so active low basically means, so we have seen this, right? This pin is active when it is low. Low means 0. Remember, low means 0 volts or binary 0. High basically means 5 volts if you are looking at it from an electronics viewpoint. If you're looking at it from a digital viewpoint, it means 1. Okay, that's what it means. Look at this. If you look at this, so look at this read. So on top of the read pin, you have the bar. The bar basically, sometimes this is written as this, sometimes it's also written as read dash or a hyphen on top of read. This basically means whenever the input here is low, whenever the input is 0, we are going to go into a read mode. Okay, so this is called active low, which means this pin is going to be active when it is low. So for example, in this chip, right? So in 8085 chip, let's look at so look at write. There is a special pin for write also. It is also active low, right? So again, there is INTA. Again, these are basically interrupt based chips, interrupt based pins. We'll learn about what interrupts are little later. But if you look at this pin, 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 right? All of them have a bar on top of it. Sometimes they are also written with a dash to imply that those pins are active when they are low. By default, if nothing is not, if so, for example, active high basically means the other pins. Look at this. Look at any of these pins, right? Look at ALE pin here. Look at this ALE pin here. Look at this pin. This is active high, which means when it is 1, this pin is active. We'll learn what ALE is in a little while, right? Similarly, look at this reset pin, RST 7.5, right? Again, each of these pins have their own meanings, as again, different microprocessors will have different sets of pins. What we learn in computer organization and architecture is a general set of pins that are common across multiple microprocessors and how they help us get our work done. Right, so active high pins are like your ALE pin, right, which are high when it is 1, right? So active low basically means when they are low or when they are 0, they are active. Active high means when they are 1, they are active high. By default, everything is active high unless otherwise stated, right? So this ALE doesn't have a bar on top of it. That's why it is active high. Very simple concept. Then there is this concept called as time multiplexed pins. Again, the same diagrams I've copied here. Okay, so then there is this concept called as time multiplexed pin. This is a very interesting idea. Look at your 8085A processor. You have these pins. Look at this, AD0 to AD7. So if you look at it from the perspective of 8085A processor or 8085 processor, you have AD0 to AD7, right? Then if you look at these address pins, you have A8 to A15.
So now we've seen what all address bits are there, right? So let's understand a couple of things here. Look at this. Your AD0 to AD7 is here. Your AD8 to AD15, your A8 to A15 are here. Now there is a small difference in naming. Here your address bits are A8 to A15. Here they are AD0 to AD7. Why is the difference there? Number one. Number two, do you see the data pins anywhere? You have seen these 16 address pins. So how many address pins do we have? We have 16 address pins here, right? So we have 16 address pins. What does that imply? 16 address pins, which means my address size is 16 bits. Which means what is the total address space that I have? 2 power 16 cells or 2 power 16 words, right? And 8085 is an 8-bit processor. 8085 is an 8-bit processor, which means any data that we copy into the processor or out of the processor is 8-bit. Which means what is the total? So if you have a memory where one word equals to 1 byte, because anyway this 8085 processor only reads 1 byte at a time because it's an 8-bit processor, because it's an 8-bit microprocessor, right? So what is the total memory size that I have? 2 power 16, each cell is 1 byte or each word is 1 byte. So 2 power 16 bytes. What is 2 power 16 bytes? 2 power 6 is 64. 2 power 10 is 1 kilobyte. So this is the total address, this is the total maximum addressable space. This is the total maximum, this is the maximum size of the main memory on my which I can connect to my 8085A microprocessor. Very simple concept. But here comes the question. Look at this. There is a naming difference here, right? So what happens? So these pins AD0 to AD7 are called as time multiplexed pins. Why are they called multiplexed? Because these pins, because look at this. What is our address? Our address is A0 to A7, A8 to A15. This is what my address is. My address is a 16-bit address, right? What about my data now? Again, this is the lowest bit. This is the highest bit, right? So what is my data now? My data is D0 to D7. Why is it only D0 to D7? Because it's an 8-bit microprocessor. Because this microprocessor only transfers 1 byte or 8 bits at a time. Because it's an 8-bit microprocessor, my data pins are only D0 to D7. Now if you look at the naming here, this is AD0 to AD7. And I don't have D0 to D7 anywhere. If you see here, I don't have D0 to D7. So what happens in the case of 8085A microprocessor, which is very similar to 8085 microprocessor, is these same 8 bits are used sometimes to represent address 0 to address 7. Sometimes they are used to represent D0 to D7. That's what is called multiplexing. What does multiplexing mean? It means the same pins are used for multiple to represent multiple things at different times. Now the big question obviously in your mind is, how do I know that whatever data is, whatever values are there on these pins, their addresses or their data? How do I know that? You can know that from this ALE pin. This ALE stands for address latch enable. This stands for address latch enable pin, right? So whenever ALE pin is 1, so let me write this down here. If ALE pin is set to 1, that means whatever value, whatever you see on this AD0 to AD7, that is interpreted as an address. Okay, so whenever you have ALE set to 0, ALE is just one of the pins, right? Whenever ALE is set to 0, these pins, whatever bits are there or whatever values are there, they'll be interpreted as data. Remember, whenever this microprocessor connects to a RAM, look at this microprocessor connects to a RAM, right? So what happens if you look at the step-by-step part? First, the microprocessor sends the address. First step is send the address. First step is send the address. The second step is copy, read or write the data. Read or write data from the RAM. So which means these two do not happen simultaneously. First we send the address. When we are sending the address, we'll make our ALE value set to 1. We'll set our ALE value to 1, send the address, because when I set my ALE equals to 1, these bits are now, whatever data is here, it is treated as an address, right? Now, after I've sent the address, right? If I want to write or read data to it, then I'll make my ALE to 0. Then whatever is here is now being interpreted as data. Okay, this is what is called time multiplexed pin. And why is it called multiplexing? Because the same pins are used for two different tasks at two different times based on the value of an other pin. Very, very important. And we do not use the same pins for both the tasks at any time. Because if you look at the sequence of steps, first we send the address, then we read or write the data. Right? That's how the whole thing works. Now if you look at the 8086 processor, this is another very popular processor. If you look at the 8086 processor, let's look at what all it does have. It has AD0 to A19. Look at this. It has AD0 to AD19. So AD0 to AD15. Look at this, AD15. After AD15, it has A16 up to A19. So now what is the size of the address? What is the size of the address of the 8086 processor? 20-bit address. 20-bit address, right? Because again, these 16 bits are multiplexed. Remember that 8086 is a 16-bit microprocessor. It's a 16-bit microprocessor, right? So which means its data is going to be 16-bit. Its data is going to be 16-bit. Those 16 bits are multiplexed with the lower bits of the address. The address consists of 20 bits. A0 to A15 are multiplexed with D0 to D15. That's how the multiplexing works here. Okay, that's how exactly it works here. Right? So that multiplexing is already happening here. The A16 to A19, they are not multiplexed with data. Right? Because the address is 20-bit, how many words or how many cells can I have? I can have 2 power 20 cells. See, if this is connected to a RAM, what is the maximum size of this RAM or main memory? 2 power 20 cells, right? What is 2 power 20? 1 mega cells or words, right? And what is the size of each word? Each word can be 16-bit. Each word can be 16-bit because my 8086 microprocessor is a 16-bit microprocessor. So one word could be at most 2 bytes. So one word could be 2 bytes, which means I could have 2 megabytes of memory that I can address totally. That's a total addressable memory size that I can address using an 8086 microprocessor. Right? Very interesting, right? And I have 16-bit data that is multiplexed with the A0 to A6. So A0 to A15 is multiplexed with D0 to D15. There is also another form of multiplexing here in 8086 processor. 8086 processor can work in something called as max mode or min mode. Again, as you keep going towards more modern processor, the complexity of the processor itself increases, right? See, 8085 and 8085A are very, very simple processors. 8086 is one of the slightly more complex processors. If you keep going to i5, i3, i7, i9 processors, they become far, far more complex, right? So what it does is, so you have a bit here somewhere called so look at this. You have this bit. It's called the min or max bit. If this is set to 0, we are set to be operating in max mode. If this is set to 1, this whole chip is set to be working in min mode. If we are working in max mode, this is what these pins represent. Look at this. If you are in max mode, this is what these pins, look at these pins. These pins are also multiplexed pins. These pins represent these signals. Okay, again, these are different signals, lock signal, S2, S1. Again, each processor has lots of special purpose pins of its own requirement. Okay, but if you're operating in min mode, if I'm operating in min mode, the same pins are interpreted as hold and M by IO, DT by R, other things. Look at this. Your ALE is here. So you might wonder, where is the ALE here? Here there is a very clear ALE pin here. Here there is no ALE pin. So how do I know that I'm operating in the ALE pin? First, I have to work in my max mode. I have to work in my min mode, which means I change this pin to value to 1. The moment I change this pin value to 1, then this pin, this 25th pin is interpreted as an ALE pin. And we learned what is ALE pin, right? ALE pin helps us understand whether this multiplexed address and data pins are being used to send an address or they're used as data pins, right? So your ALE is here, okay? So again, here in addition to the address and data multiplexing, there is also max mode, min mode multiplexing that happens on 8086 microprocessors. Again, there are a lot of other things that I'm not going into right now, Because they're very architecture specific. They're very specific to the 8086 chip. Again, we'll understand some of these interrupts, all of that stuff we'll understand as we progress through the course. Okay, in the context of address and data, they're not very important, right? I hope you got a good sense of this. Now, how does the address latch itself work? Look at this. So in our final interfacing, okay, if I want to interface my CPU to memory, there are three components here. There is the 8085 microprocessor. There is a microprocessor, it could be any microprocessor. There is the main memory or RAM that I use. There is a third chip called the address latch chip. Address latch chip. There is a third chip. We use all three of them to actually connect the CPU to memory in reality. So we have learned about the microprocessor, the multiplexing in the microprocessor. We learned how RAM itself works. We know that. Now let's see how the ALC itself works. It's called the address latch chip. What it does actually internally, you might have learned this in your digital logic design. Internally, your address latch chips are nothing but flip-flops. They're actually flip-flops. Again, we have covered flip-flops extensively and the internals of how flip-flop works in the digital logic circuit and digital logic design course, right? So internally, your address latch is nothing but a bunch of flip-flops. And the way it works is very important. It's also a chip, right? What it has, the address latch chip itself has four very important things. It has something called as a strobe. STB stands for strobe. I'll explain you how all of these work. Okay, STB stands for strobe. OE stands for output enable. It stands for output enable. And remember, this is an active low pin. That's why there is a bar on top of it. This is an active high pin. Then you have a bunch of input lines. You have a bunch of input lines and you have a bunch of output lines. Okay, that's all there is. So the way the whole thing works is this. If my strobe equals to 1, again, the chip internals, how the chip internally works, internally it's a bunch of flip-flops. That's what it is. But let's see how it works as far as the input, output, STB and OE are concerned, right? When the strobe pin, when the STB pin can be 0 or 1. When the strobe pin is 0, then the input lines are disabled. This implies that input is disabled. So I do not read whatever is the input here. See what this address latch literally does is it reads the data from the input. It stores this data internally using a bunch of flip-flops, and whenever I want, I can send it through the output. That's what exactly it does internally. So when the strobe pin is 0, that means the input is disabled. I'm not reading whatever is the input into my memory, which is here. When my strobe pin equals to 0, that means input is enabled. So whenever my strobe pin equals to 1, whatever is the input bits, okay, all that information, I'll read it and store it in the memory here, right? Next, your OE, look at this. Your OE is an active low pin, right? It's an active low pin, which means when it is 0, it is active, which means OE basically means output enable. So when this is 0, output is enabled. Which means whatever is there internal, whatever is stored as part of this address latch is now visible. All this data now flows through this output. So you can think of address latch as temporarily storing the data here. You can think of it literally as whenever I get some input, if I want to store this input, I'll make my STB equals to 1. That input is stored. Then I make my STB equals to 0. If I want to read this output on the output lines, I make my OE equals to 0. So output is enabled. When this is 1, output is disabled, which means whatever output is here, no output comes here literally. Output is disabled. And look at it. Why is it the opposite logic? Because it is an active low. When OE is low, output is enabled. When OE is high, output is disabled. Very simple logic here. This is called an address latch chip. Now the whole interfacing works as follows. This is the most important diagram. So let's go through this step by step. So let's assume I have a microprocessor here, right? Let's assume I have a microprocessor. Let's say 8085 microprocessor. Again, these are the registers that I have in my microprocessor. As we discussed earlier, every microprocessor has some memory internal to it. We discussed this, right? We discussed it when we understood how the move thing works, right? I told you that there is internal memory within the CPU called as registers. So let's assume this this microprocessor itself has some registers. There are some special purpose registers like accumulators, but there are a bunch of registers. This is memory within the microprocessor. Okay. Now look at this. Let's assume this is my main memory or RAM chip. This is my ALC chip. Let's look at all the connections and understand. Okay. First and foremost, this is write. This is active low. So this write is connected to this write. Both of them are active low. So whenever this chip wants to write data to RAM, this will make this equals to 0. That 0 is passed through this, and this will also go to the write mode. Again, this is read. This is also read. Whenever this microprocessor wants to read data from RAM, it will make the read equals to 0, and the same 0 is passed here. As soon as this is 0, the RAM goes into the read mode, where it starts, whatever address is here, it will start sending that data back to the CPU. Okay. Now look at this. There is the ALE. There is the ALE pin. We connect the ALE pin to the strobe pin here. Now this is very important. Look at this. When the ALE pin is set to 1, what happens? Look at this. What all am I connecting between the microprocessor and the ALC or my address latch chip? What am I connecting? This OE, I'm setting it to ground. Remember, in electronics, ground means 0 volts, which means this is always 0, which means output is always enabled. Look at this. Output is always enabled here. That's very important. Okay. That's the first part. Okay. This is not the end of it. This is just the starting of it. Oh, I've connected the OE to ground, but I forgot to connect the output pins here. So there will be a bunch of output pins also, right? I forgot to connect them. Sorry. So let me connect them. So these output pins will connect to A0 up to A7, right? So these output pins will connect to A0 to A7. Okay. So this is how it will flow. Okay. I forgot to connect them. Okay. So let's look at this ALC. This ALC has the strobe pin, the output enable pin. This is my input pins. All these are my input. Let's assume it has 8 inputs and 8 outputs. So these are my inputs and these are my outputs. So look at how I'm doing it. This is very, very important. So the microprocessor will set this ALE to 1. The moment it sets this ALE to 1, what happens? The strobe becomes 1. The strobe also becomes 1. When the strobe becomes 1, what happens? When ALE is 1, what does it mean? This, look at this. These are multiplexed, right? When ALE is set to 1, what happens? The address is sent through these 7 bits and also through these 8 bits and these 8 bits. Between these 16 bits, across these 16 bits, right? Across these 16 bits, address is now sent when ALE is set to 1. Look at this. This A8 to A15 is directly connected to the A8 to A15 of the RAM. Remember, the RAM also has 16 address pins. The RAM also has 16 address pins and 8 data pins. The RAM has 8 data pins, right? Because it has 16 address pins, let's also assume that one word equals to 1. Because it has 8 data pins here, one word equals to 1 byte. What is the total size of the RAM itself? Because it has 16 pins, right? It has 64 kilo into 8 RAM. That's what this RAM structure is. Right? This is the capacity of the RAM itself, right? Now look at this. When I set my ALE equals to 1 and pass these addresses, this A8 to A15 directly go into this. Cool. But what about A0 to A7? So as soon as ALE is set to 1, whatever data I'm sending in here moves through this, goes to the input. My strobe is also set to 1 because strobe is connected to ALE. ALE becomes 1, which means strobe becomes 1. So all these addresses, when ALE equals to 1, what happens? My addresses, this behaves as if I'm sending an address. These addresses are now the input to my ALC, to my address latch circuit or address latch chip, right? So, and again, because my OE is always grounded, OE is always set to 0, whatever input comes in, gets stored here internally, and the same input is passed to the output. Look at this. Whatever address is being sent here, it is copied internally. Look at this. All these 8 bits of address is copied internally. When it is copied internally, this OE is always set to 0 because it's grounded, right? Ground in electronics means 0 volts. In binary, it means 0. Because this is always set to 0, the output is always enabled. So here we are copying these 8 bits of address into the ALC and we are passing it to this address. Now what happens to the address bits now? I got the actual address that I want because these pins did not behave like data pins. They behaved like address pins because ALE is 1. So the address is now given to the RAM. Now given that I have sent the address first, Now I want to either read or write data. Now to do that, what should happen? To do that, very importantly, to do that, my ALE should become 0. My ALE becomes 0. Look at this. My AD0 to AD7, my AD0 to AD7, they're also connected. So whenever I have this thing, it means this wire is going on top of this wire. Okay, we draw this in electronics, we draw it like this to show that this wire and this wire are not touching each other. Okay, so AD0 wire goes and gets connected to D0. Your AD7 wire gets connected to D7. And when ALE is 0, look at this, when ALE is 0, what gets passed here? Data, not the address. Not the address. But these address pins, look at this, these 8 address pins of the RAM, they get the address because the address has been stored in the ALC. This address has already been stored in the ALC. Now when ALE becomes 0, what happens? Whatever inputs are here, they are not taken by the ALC. That's what we said, right? When strobe equals to 0, the inputs are disabled, which means these inputs are no more read into the memory which is stored here. Right? So what literally happens here is this, very simple. So these addresses, because my ALE is 0 when I'm using them as data pins, this is 0, which means strobe is 0, which means these pins input will not be taken into the ALC. So whatever values are stored in the ALC are given to the address pins. So now I have the address pins. Now whatever data is passing through these pins, because ALE equals to 0, are connected to the data pins of my RAM. This is how the whole interfacing works. Very, very important to understand this structure, right? So this is how the whole, again, we need 3 components here. We need the main memory, we need ALC, and what is ALC doing? ALC is helping us to copy the address values into the chip and keep providing them to the RAM. And at some point when I don't want to use them as address pins but want to use them as data pins, I can use them as data pins. No problem. So all of your time multiplexing is being enabled because of the ALE pin, because of this actual pin based multiplexing, and because we have ALC. ALC enables you to successfully perform time multiplexing on the chips. Now you might say, why are we even doing time multiplexing? Why can't I just create new pins? Why can't I create 8 more pins? More the pins, larger the chip. Look at this, more the pins, more complex the circuit will become. Again, remember this, you have to place this on an actual motherboard or an actual chip, right? Or actual printed circuit board. And more pins, more complex it becomes. So microprocessors, even today, there is a lot of time multiplexing that happens even on very, very advanced microprocessors like i3, i5, i7 microprocessors. That's very important to understand. Now there is another concept which is very related to this. With this, we'll understand how the whole thing works literally, right? So there is something called as a clock cycle. This is something that you may have learned in your digital logic circuits, but I thought I'll cover this briefly for you. Now look at this. Whenever you buy a microprocessor, you say this microprocessor has some clock speed. 8085 microprocessors have a clock speed of 3 megahertz. The modern microprocessors typically have 2 gigahertz to 4 gigahertz. I mean, consumer grade. If you buy a high-end Intel microprocessor today, i3s, i5s, i7s, i9s, you'll see 2 to 4 gigahertz. You'll typically see 2 to 4 gigahertz processors, right? So what does this mean? This means actually inside every microprocessor is connected to a clock, to a clock. Okay, this clock ticks at this frequency. As every microprocessor is internally connected to a clock, and a clock actually ticks like this, right? So the clock also goes from 0 to 1 to 0 to 1. So this is what is called as ticking the clock, right? So now this is a clock like this, right? So what happens is, in a modern microprocessor, let's assume the microprocessor is operating at 2 gigahertz speed. This is often called as the speed of the microprocessor, right? Often used, I mean, in colloquial language, whenever we try to buy a microprocessor, we say, hey, what is the speed of the microprocessor? Somebody says 2 gigahertz, 3.7 gigahertz, 4 gigahertz, etc. So let's take a microprocessor which is operating at 2 gigahertz. This is the frequency, right? What does it mean? It means it is performing, what is giga? Giga is 2 power 30. So this is what this means, right? So the frequency is 2 into 2 power 30 hertz. 2 power 30 is roughly equals to 10 power 9. Right? That's what we saw this, right? 2 power 30 is roughly equals to 10 power 9. So which means So this is called as a cycle. Look at this. If from this time, so if you think of this as a time axis, this is called, so from here to, so it stays up, goes down, stays down, and goes up. So from here to here, this is called as one cycle. This is called one cycle of the clock, right? This is called as one clock cycle. So one clock cycle is from the time it has become high. So let's assume this is high or 1, this is low or 0. From the time it has become 1, it will stay high for a while, then it will go down, then it will stay down, and it will go up. So this whole thing is called as one cycle, right? So this is called, again, this is a digital clock, right? You might have encountered sinusoidal waves. Look at this. You might have learned in physics about sine waves, right? So sine waves are analog waves, right? So here what is it? So look at this. Going from this point back to this point is one cycle. You might have learned this in your physics, right? So this is called as one cycle. You go up, you go down, and then you go up again. So this is called as one cycle for an analog wave. This is a digital wave. Again, this is something that you may have encountered in your digital logic circuits. This is called as one cycle, right? Now 2 into 10 power 9 basically means, 2 into 10 power 9 hertz basically means this processor's clock actually operates at, it can do 2 into 10 power 9 cycles per second. Hertz basically means, this implies 2 into 10 power 9 cycles per second. That's what this means. Okay, it can do these cycles 2 into 10 power 9, right? Now what does that mean? It means this width in time, this is called the time interval of one cycle, or one cycle time. This time is now equal to 1 by 2 into 10 power 9. What is this? This is 0.5 into 10 power minus 9 seconds. What is 10 power minus 9 seconds? 1 nanosecond. So 0.5 nanoseconds. Remember, what is a millisecond? A millisecond is 10 power minus 3. A microsecond is 10 power minus 6. A nanosecond is 10 power minus 9. Right? So again, very, very important to know these terms. You might have learned this in your physics or in your science classes in your 10th or 11th class, right? So just wanted to cover that. So this processor, remember, this is very important. This is called as a clock cycle. This is what is called as a clock cycle. This one thing is called as your clock cycle or simply cycle. Now, remember, if your CPU can operate at a higher frequency, imagine I have a CPU, I have one CPU that operates at 2 gigahertz. I have another CPU that operates at 4 gigahertz. Every CPU instruction, we have seen CPU instructions, right? Like move, right? So like increment, we have seen these CPU instructions. Every CPU instruction takes one or more clock cycles, right? So the more clock cycles, the higher the frequency. Imagine I have processor 1 and processor 2. Imagine I have a processor that operates at 4 gigahertz, which means it can do these cycles faster because it can do more cycles per second. See, the 4 gigahertz processor does double the number of cycles than your 2 gigahertz processor. And let's assume the move operation, let's just say the move operation requires 4 clock cycles. I'll explain you how one of these operations works in a little while. Let's assume the move operation by the microprocessor requires 4 clock cycles, right? Very simply. Now, if the processor is working at 2 gigahertz, how many nanoseconds does it need? Because it requires 4 clock cycles, 2 gigahertz, right? 4 clock cycles. The 2 gigahertz processor will need 4 into 0.5 nanoseconds. So which means it requires 2 nanoseconds to complete. At the same time, the 4 gigahertz processor, what is the time interval for the 4 gigahertz processor? It will be 0.25 nanoseconds. So it will require only 1 nanosecond to complete the move operation. So the higher the clock speed or higher the frequency of the microprocessor, the faster you can execute. That's why every time, whenever any major company like Intel or AMD or ARM, some of the biggest manufacturers and designers of microprocessors, or even a Samsung or any smartphone, even see this in smartphones, right? Whenever a new smartphone microprocessor or a smartphone chip is launched, they tell you about the speed at which it can operate, because the higher the speed, the faster it can operate, right? So the speed is a measure of how fast your processor can run, right? So this is what your clock cycle is. Now, since we have understood what is a clock cycle, is the cycle time. So this is nothing but 1 by frequency. You can think of it as 1 by frequency of operation of the microprocessor. It is the frequency of operation of the microprocessor. This is very, very important. Understanding this concepts of clock cycle. There is also a concept called as machine cycle. Okay, let me explain this. Machine cycle in a nutshell is nothing but it is a number of clock cycles. It is a number of cycles. Again, we'll use the word cycles to just represent clock cycles. It is a number of cycles required. So a machine cycle is basically the number of cycles required to complete an operation. To complete an operation. Look at this. I told you just a while ago, right? That let's assume that an operation like move requires 4 cycles. Now what are those 4 cycles? Let's try to understand that. So let's take a machine instruction, because we've already seen move and increment. Let me introduce you to a new machine instruction. This is called as LDA, and there is a memory address given here. LDA basically means load into accumulator. LDA basically means load into accumulator. Now accumulator is a special accumulator. Look at this. When I was explaining with this, right, registers, there is a special register in the microprocessor called as an accumulator. It's a special register which is used for special purposes by the microprocessors, right? So LDA basically means whatever is the data that is in address 2080 on your main memory, load those 8 bits of data, in this case 8 bits, because we are talking about 8085 microprocessor. Let's assume this is being executed on an 8085 processor, right? Whatever 8-bit data is there in this memory location, copy that into the accumulator register. So load it into the accumulator register. Accumulator is a special type of register. Now how does this, again, this is just one instruction. This is just one instruction. But this instruction could take multiple clock cycles. Let's see how the clock cycles themselves work, step by step. Okay, this is very important to grab it. So in the first cycle, so let's assume I have these cycles. Let's assume this cycle, so let's start from here, right? Let's start from here. So let's assume this is my cycle T1. Okay, so this is my cycle T2. Then from here to here, let's assume it is my cycle T3. From here to here, sorry, from down, up, down, up. Or else let me draw it here itself, just for clarity. So imagine I have my clock cycles like this, right? So let's assume I have my clock cycles like this. Okay, so my first cycle starts from here. Okay, let's assume I'm at this time right now. My first cycle goes from here to here. So let's call this cycle as T1, cycle T1. Then my second cycle goes till here. Let's call this T2, right? So my third cycle goes from here to here. So this is my third cycle. Okay, let's say this is my fourth cycle, fifth cycle, and so on and so forth. In each clock cycle, the microprocessor does one task. It breaks this. Look at this. This is just one instruction. One instruction could take one or more clock cycles. An instruction like this, okay, an instruction like this could take multiple clock cycles. Probably in cycle, again, I'm just giving an example here. I'm not saying this is exactly what happens in 8085 processor. I'm just giving you a general idea here, right? So in cycle T1, okay, in cycle T1, the address, this 2080 address is enabled. So what do we do now? We send the address first to the, look at this. This is our interface, right? First we have to send the address. Only then I can get the data from that address. So in the first clock cycle T1, I send the address. How do I send the address? Very simple. I set the ALE to 1. Again, this address is 2080, right? 2080. Again, let's assume this address is in hexadecimal, just for simplicity, so that I can read it as four nibbles, because one nibble is 4 bits, right? So let's assume this address is in hexadecimal. Then what are my addresses? AD7 to AD0, right? And I have A15 to A8. This, again, remember, this is in our 8085 architecture. These are time multiplexed. So I've set my ALE to 1, which means they'll be interpreted as address pins now. I need to send the lower values here, right? So 80 in hexadecimal will be sent. Here 20 will be sent in hexadecimal. So I'll actually copy this value 20 in binary. This is in hexadecimal, right? I'll convert this into binary. This will become 16 bits. This will become 4 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 bits. That's how you convert from hexadecimal to decimal. And in my first time interval, or in my first clock cycle, or in this time interval, because in this, look at this, your CPU is operating at this clock speed, which means in this time interval, my CPU can enable my ALE to 1. It also can send all of this information, right? That's all it can do. So this is my send the address in T1. Now let's go to send control signals. I've sent this. Now I have to also send control signals. What are my control signals? Now after this, I need to make my ALE equals to 0. Now as soon as my ALE is set to 0, okay, this happens at time T2. This happens in my cycle T2. In cycle T2, what do? I make my ALE equals to 0. As soon as ALE equals to 0, whatever address I have sent earlier, that is already copied into this ALC, into the address latch chip. It's already copied into the address latch chip. The same values will be here. So as far as the RAM is concerned, it is seeing all of these 16-bit addresses, even though this is not sending addresses anymore. Because whatever address it was sending earlier, we copied it into the address latch chip, and we are now making the same values visible here because my OE is set to 0. Right? Very simple concept till now. Okay. So my T1 is done. In my T2, what I do now is I make my ALE equals to 0. And I also send, suppose if I want to write data. Suppose I want to write data, let's say. Sorry, I want to read data, right? So what does this do? It says load into accumulator. So I want to read this data. Okay. Because I want to read the data, what should I do now? My read pin, because it's an active low pin, I'll make it equals to 0. So my read pin equals to 0 means I want to read the data. This is on the chip. This, again, remember, the moment I make my read equals to 0, my RAM also will go into the read mode. When this is in read mode, I can't have write, which means write. Again, I'll also make my write go to 1 because it's also active low. WR dash equals to 1 means it's not going to write, it's only going to read. Right? The second timestamp. The second clock cycle. In the third clock cycle and the fourth clock cycle, remember always, this is a very important observation. Your RAM chips run at a much lower clock speed than your processors. Typically modern processors operate at 2 gigahertz to 4 gigahertz. Of course, there are microprocessors which can run at faster or slower speeds. This is your microprocessor clock speed. Your main memory or RAMs, they typically work at something like, again, 1444 megahertz is a very, very popular configuration. What is 1444 megahertz? This is roughly 1 point something gigahertz. Right? Because 1024 megahertz, remember, 1024 megahertz is equal to 1 gigahertz. Right? Again, if you're using the giga mega thing, or else if you don't want to do all of this confusion, if you just want to use 10 power 3 base notation, this will become 1.4 gigahertz. So you could have a processor that is operating at 2 gigahertz or 4 gigahertz, which is connected to a main memory or RAM that is operating only at 1.4 gigahertz. Right? So what happens? Your main memory typically runs slower than your microprocessor because designing the underlying electronics of main memory that operates at 2 gigahertz or 4 gigahertz is very, very expensive. There are some main memory that can operate at 3 gigahertz also. There are some main memories today which can operate at this speed, but they're way more expensive. Okay, because again, your main memory is fairly large in size. It is either 16 GB or 8 GB or 32 GB, right? So because of the electronics limitations, designing main memory that works at very high speeds is very expensive. So typically in the real systems that we often use, I'm not talking about some outlier systems. In the general systems that we use, our RAMs tend to work at a lower clock speed than the microprocessor. Remember, your RAM also has a clock that it works with, which means it can only send data at that frequency. Because remember, your RAM operates at a lower frequency than your microprocessor. It might require multiple microprocessor cycles to read the data from the RAM. Because RAM is a slower device. Remember, RAM is a slower device than your microprocessor. That's why accessing data from your registers is faster than accessing data from the RAM. Right? Because registers are operating at the same clock speed as your microprocessor itself. You can actually access registers at the clock speed of the microprocessor, but the RAM itself is slower. So whenever, till now we have been saying, right, accessing data from the RAM is slower than accessing data from the registers. Why is it so? Because RAM's internal clock at which they work, at which they operate, is slower than the clock speed of microprocessors in most real world applications. So it might take 2 clock cycles. Again, this T1, T2, all these clock cycles are microprocessor clock cycles that we're talking about. So let's assume that my main memory is working at half the speed of my microprocessor. Let's assume my main memory is working at 1.4 gigahertz and my microprocessor is working at 2.8 gigahertz, which means my microprocessor is operating at double the speed of my main memory. So which means, now look at this, I've sent all of this information. Now my main memory, this is very, very important, right? My main memory will take some time. If my main memory is operating at 1.4 gigahertz, it will take some time to place the data that is there on the data lines, right? It will take some time. In that time, look at this, because it will take some time, right? And at how much time does it take? How much ever is the cycle time of the RAM itself. And since RAM is operating at half the speed, look at this, RAM is operating at half the speed. So by the time the RAM actually places the memory values on the D0 to D7, by the time the RAM places this, because the RAM is operating at, let's say, half the speed of my microprocessor. By the time it places, my microprocessor, already 2 cycles have happened, because my microprocessor is operating at double the speed, right? My microprocessor is operating at double the speed, right? So what happens here is, by the time my microprocessor, see, look at this, my RAM might be operating like this. My RAM speed might be like this. Let me draw it here. Okay, my RAM may be operating like this. Okay, at half, see, by the time it finishes 2 cycles, this will only finish 1 cycle. Okay, and so on, because it's operating at half the speed with this simple example, right? So by the time my data is placed on my data, on my D0 to D7 pins, look at this. By the time my data is placed on this D0 to D7 pins, this has already done 2 cycles, but that's okay. That's okay. We know that it will take us longer time to copy data from RAM to the processor than from the registers. We know that, right? So the processor waits for this data to be present, right? So during T3 and T4, it will keep waiting for the data to be present in D0 to D7. At the end of T4, as soon as the data is available, it will copy this data and store it in the accumulator register. Look at this, as soon as the data is available here, it can copy it to the accumulator, because accumulator storage operates at the microprocessor speed, right? So this whole thing is called as the machine cycle. It's very, very important to get these concepts right. A clock cycle, again, remember that most RAMs are slower than your microprocessors. If you open up your laptop or even your smartphone and see what is the processor speed, you'll see speeds like this. If you look at your main memory or RAM speeds, you'll see speeds which are typically like this. Of course, there are faster RAMs that are coming into the market, but they're very expensive. Okay, so this is how the whole memory CPU interfacing works, and this is the clock cycle logic. This is the machine cycle. This is the machine cycle for transferring some data from memory to a special register called accumulator. Similar logic is there even for move, increment, any operation or any machine instruction or any machine instruction here is decomposed into a number of cycles, 1 or more cycles, right? For example, let's take this, your increment operator, right? So imagine if I have this. Imagine if I have another instruction, right? Increment accumulator. Okay, how many cycles do you think this would need? Logically, I'm not asking for a perfect answer, because the accumulator is already there in the accumulator data. The data in the accumulator is already present in the RAM here, right? My incrementing from the accumulator doesn't require me to read data from the RAM. The data is already here. I want to increment this. So the CPU itself, the CPU broadly has two broad units. One is called the control unit. The other is called the arithmetic logic unit. The arithmetic logic unit actually performs all arithmetic and logical operations. So this incrementing of the accumulator can be done in far fewer than 4 cycles, because I don't have to wait for the RAM to send me data, and RAM is a slower device. All of that I don't have to do, because the data is already there in the accumulator. and I can access accumulator almost at the same speed at which my processor is operating. So in one clock cycle, I can actually access this. I can increment this literally probably in 1 or 2 clock cycles, depending on the architecture of the microprocessor itself. And the arithmetic logic unit, which is again, my CPU itself broadly has 2 components. Control unit, arithmetic logic unit. We'll understand this in lots of depth as we progress through this course, right? Just wanted to give you that idea that multiple instructions will require multiple number of clock cycles. Again, when I say clock cycle here, I'm only referring to my CPU or my microprocessor clock cycles, not to my RAM clock cycles.